So, moving beyond porcelain and everything like that, can you give us an example of a modern engineering ceramic that has a significant impact in our world today? You had mentioned earlier this idea of casting cores, and
Yep.
if you want to dig into that a little bit more.
Sure. So casting cores are traditionally silicate based. And what's really interesting about this ceramic, and so as I mentioned earlier, they are used to form the cooling passages in metal. So in the metals that I'm talking about are nickel superalloys, which in hot gas pass are single crystal nickel superalloys for the hottest hot gas path turbine components. For example, a stage 1 turbine blade. To make the cooling passages in that stage 1 turbine blade, you would need a casting core that had a silicate type of composition. What's interesting about these casting cores is that unlike other ceramics, which you think of as strong, you want strength but not too strong. You want to be able to get it out at the end of the process of casting your metal. And to do that, you have to use an autoclave in a caustic environment and pressure and basically like pumping this ceramic out of the metal at the end of the day. So if it's a really strong ceramic, you won't get it out, and then you won't have your air passage. If it's too weak, it won't survive the casting process. And the way the casting process works is first you would basically take your casting core and then you would wax over that core to form the shape of the metal. And so it's basically the lost wax process. And so you need to be able to form a ceramic shell that will define the outer surface of your metal blade with the core inside. And to do that, you have to use a wax process. And then once you have your wax on top of your core, you will shell, and that is also a ceramic, and that is usually a layered ceramic process. And that forms the outer shell that holds the metal in when it is liquid and poured into your mold. And the shell is also a mold. And so then after you shell, you want to put that into an autoclave and you will remove the wax. You will have fixturing to keep the ceramic core in place. So you can imagine it looks like a ceramic shell, some air gap, that will eventually be metal, and your ceramic core, which will eventually be air. And then you will bring that to a casting furnace where you would basically pour in your liquid metal, and there will be a thermal gradient where you will slowly draw and create a single crystal metal out of that melt. You basically seed it in the direction, you have a seed and you have a grain orienter to basically make sure you have the right orientation of your grain. But at the end of the day, you'll have a single crystal metal and you will have your core inside your metal. And then you need to remove your casting core once everything cools and you remove your metal from the furnace. You remove the shell, you remove the core by putting it into an autoclave, and then you will use an EDM or a similar tool to basically drive holes through the metal to the cooling channels. And then that is how you basically connect the cooling channels to being able to film cool the surface of your metal during operation. It is a complicated process and it is not cheap. and at the end of the day, the ceramic that forms the core inside of that process has a complicated pattern. They are made through a couple of different processes today. One process is basically high pressure injection molding, a very precisely machined metal die with a ceramic. Another process is directly printing the ceramic using 3D printing. And so that is a way that is being explored on how to make those casting cores. And you could go to different 3D printing websites like Lithos or Admatech and see that they have casting core examples that are made by 3D printing. And I just think that's fascinating because how we form ceramics is also changing. And one of the barriers of changing a cooling pattern in the turbine industry is how long it takes to machine those very precisely machined dies for making the injection molding of the ceramic. And so this is a dynamic market right now and things are changing fast, and it's something to keep an eye on.
I think that's another great example of sort of what we had discussed earlier where, a lot of these applications are, aside from lightwares and all that, is very far back in the supply chain. And it's not something that, something we take for granted in modern life, but is super important nonetheless. And so to dig into that a little bit more, how is the microstructure of these casting core materials, how is this microstructure engineered to meet this sort of Goldilocks zone sort of requirement in terms of these properties that you mentioned? Because it sounds hard enough to make a ceramic that's, super, super strong. It sounds hard to make a ceramic that's super soft for various applications, but it sounds a lot more difficult to make something that's just in the middle and just right.
It really is. And one thing to remember is that it's touching a molten metal.
Doesn't help.
And not all metals are created equal. And so depending on what component you're casting, it will have a different composition. Nickel superalloys have a number of different dopates in them, and they can be more reactive. Then one composition could be more reactive than another composition. And what you don't want to happen is have a reaction with the core material. And so it would be wonderful to have just an alumina core, aluminum oxide with no silica, because then you would minimize the reaction between the silica and the metal. However, the more alumina you have in the core, the stronger it is. And as I mentioned earlier, you don't want it to be too strong. And so that's where the Goldilocks comes in, right? It's got to be just right. And so there is a lot of development in mullite cores, which is an alumosilicate, to basically be a less reactive core material. So there's actually a lot of science that goes into making these cores in terms of the microstructure and the composition because of the reactivity with the metal. So it's touching the metal during the casting process. And then also, depending on the application, whether it's a land-based turbine or if it's a jet engine, it may also be touching the ceramic. The metal might be touching the ceramic and in close contact during the heat treatment. And so after you bring it out of the furnace, you may remove the core either before or after a heat treatment to anneal the metal. And so time at temperature, if you're taking thermodynamics and kinetics, you'll know that if you're going to have a reaction, if you increase the temperature, you're basically enabling that reaction to happen even faster at higher temperature. And so there's a lot of science behind carefully controlling the composition and the microstructure of that core to minimize the reactivity with the metal. Any defects in the surface will cause turbulation and you can't go in and machine those inner cooling channels. There's no line of sight to seeing them. In fact, as you go to more complicated cooling shapes, inspecting them, which used to be done with the borescope, becomes very hard, and you have to use X-ray CT imaging to actually see the surfaces and to make sure that you have a good casting, because they are so complicated today that a visual inspection is just not possible anymore.
So then what is that Goldilocks range exactly? Is it difficult to stay consistently within that? And how do these processing variations and all of these things that you were just talking about, how do they influence the ability to get within that range?
Yeah, so the core manufacturers all have their own recipes. Some of them are highly proprietary, but I will say that it's about the composition, but then also how you fire it and how you drive cristobalite formation, which is a high temperature form of silica. And so that is basically defined by your processing conditions. And so every core manufacturer will have their low fire and their high fire process defined to carefully control composition and the microstructure. And one of the outputs, or one of the things that they measure, is high temperature flexural strength or modulus of rupture. And so those are the targets that they would try to hit.